Yes, I can, and then it's ended up suddenly. Yes.
Chance the Wi-Fi. This room might have to do Wi-Fi.
Maybe.
This one, there are 80 one side. If you want to throw a Wi-Fi, that's up to you. Yeah, like as long as you're connected to the Wi-Fi, that's all that matters. But I'm not expecting to use the Wi-Fi. But if you want to,
Okay, we need something for clicker as well. USB-A. Okay, let me connect. I can't find any. I can't find any. This is just for camera, but what about clicker? Alex, sorry, Alex. For the clicker, where is the connector?
there's a good chance someone's just taken it.
What should I do? Because I'm going to.
If they don't have a clicker, just tell them they can use like the next key, like on the arrow key to move the slides.
Yeah, I have the connector, but it doesn't have any wire to connect. So.
No, okay, this isn't our clicker. This is someone has left their clicker here. So our issue with the clickers are that people will just take the clicker USBs with them. They'll just like plug it in and they just go, oh, I'm going now, and they try to put it in the bag.
Okay, they can use
if they're just happy just using the next key.
I don't know.
I mean, that's what I would prefer.
Are you happy?
Are you a presenter or yeah? Okay. Are you happy just hitting the next key to change slides, like the arrow key to change slides? Yeah. Okay.
Okay, but this one is here in case someone.
No worries. I think most people will be happy to select the next key.
Okay. Yeah. So anything else we should set up now?
Have you gone through the instructions?
Yes, I downloaded the slides. I connected these two, and we connect to the Wi-Fi, but it's I mean the Zoom, but it's disconnected. Just that.
It just disconnected again, or is it? Are you on Zoom now?
Well, in Zoom now.
Okay.
We are. I'm going to check again.
Okay. Make sure each time you come out of the Zoom that it's recording.
Yeah.
And make sure that the microphone has been set to black and white. Yeah.
Okay.
Okay. Stay here. Now I'm
connected. This to the protection.
This one should be to projection.
You can share your screen maybe. And open up PowerPoint and share the PowerPoint.
This is the. Let me see.
This is the first one, right?
This is the first one. But I did the sharing, but why it's just showing this?
You didn't share?
Okay,
Yeah.
but what about Zoom?
Zoom.
Yeah.
Open the Zoom first. Open the Zoom and share your screen and Zoom. They have a sharing, I think. Oh yeah, no, that's one. Well, our Zoom is different.
Why?
My Zoom have a bottom is share screen.
Oh my God, what should I do now? I connected from here.
Have you updated your Zoom?
Yes, it's updated. Sign in. I should sign in again.
Try. Not okay, I can use my laptop as Front laptop.
Let's see what's happened next. Hello. Okay.
Who are?
Yeah, I already joined the meeting through the Zoom in Boa. Yeah,
Oh, there's no sharing.
I'm going to leave. And we are going to check it again.
Refresh this.
And join the Zoom.
Yeah.
Okay, hello. Again.
Why? Oh, but
Okay,
we can change
from
the
the,
laptop.
no, if we change the laptop also will be the same.
The same, but
Yes.
my room has
Mm.
I room have the bottom share screen, but you haven't.
But if I connect over there also I should have something to
Just connect the volume.
no. I mean, let's check it, but leave the webinar. But I think, let's see. I think this issue is solved, hopefully.
The first slide and the shares.
Which one now? Was the slide? This one. And this.
Yeah. The
The-
plate.
Then,
Yeah.
okay, what is that?
I
Continue.
need to share. Okay, there's no.
I can see.
You can switch the screen. To,
Let me just.
Mhm. We have clicker.
No, the clicker is not working.
That's the back. This is your mouse, right?
We can't see this. Okay. Which one was that?
This one, maybe.
The question. It asks. No, I don't have mouse and it's not working.
You can just share a screen. And it's
Let
not work.
me stop it first. And then this is the screen that I'm going to share. Okay.
Yeah.
So I'm coming back to, where is my Zoom? And then I'm sharing the desktop one instead of maybe. It's not showing anything
I
currently.
think you should play the slide. Yeah, it's done, I think.
It's done.
Maybe next page. Yeah, it's done, I think. Yeah.
But the recording will be happening from your side or my side? Who is going to push the recording?
From my side.
Okay, I don't need to do anything else.
Yeah, I think so. So.
Are you the presenter? The first one? Session chair. Okay.
Okay.
Only the third one is here, right? Now, you are third one.
No, we are not presenter, we are volunteers.
Yeah.
Okay, so let me just one time more checking the instruction here
Okay.
to be sure everything's fine. Okay, and this is the connections happening. Are you the first presenter?
No, I'm the second one.
The second. Okay. Is it your, let me see. Is it yours? Is it yours? This one is yours?
Oh, yeah, this one.
Okay, I think now the all the things are okay. Webcam, Zoom, system setting, for Mac, I already did that. What else? Front laptop, open all
Yeah,
presenter.
audio is done, video is done.
Connect to big string, okay, audio off. Okay, select video to,
Real
okay, I should select the
video.
stop sharing. Video, where is video?
This one.
It's not open. Okay. Option,
On the
yeah.
camera, or second, if the camera turn on.
Is it on?
Oh, you need to
Yeah.
turn the,
Uh-huh.
yeah, turn the video. Turn. Yeah, it's on.
Okay. What else we should do? Hide caption, show hide caption light.
Yeah, I can control this from my side.
Let me check it here. Caption.
Yep.
Push.
Turn the caption. So,
This one?
click this.
Or Mac, front laptop, or Mac.
You should mute yourself.
I did that, I think.
Mm.
System settings. چطوری؟ فکر کنم که اوکی هستم. System settings. هنوز مطمئن نیستیم که مشکل، فعلا فقط داریم نگاه میکنیم ببینیم که همه چی اوکی باشه. This is built in, this is muted.
Yeah,
Okay. I think everything is done.
everything done.
Now let me go
Where's
to
the other laptop?
Yeah.
this. I'm sharing the, is it should be desktop or PowerPoint?
Doesn't matter. Because no,
I think it should be desktop.
do you use the presentation mode?
Oh, okay. این چیه؟ چجوری میتونم بهش بزنم؟
Continue to share.
نباید داشته باشه.
It's
باشه بذار کل چیز رو شیر
Yeah.
میکنم. کل دسکتاپ رو شیر میکنم.
no. You know what I mean?
بیا تو هرچی خودت میدونی. اکستندد باید باشه. اکستندد نباید باشه.
الان اوکی دیگه الان کارش کنم.
این الان داره کل همه چی رو
اوکی.
نشون میده. اوکی.
بعد This is presentation mode.
Okay. When we are going to change the presentation, it will be recorded in between because we share the whole screen.
Okay.
No, I think we should share just the presentation.
Why?
I think both is fine. I think
Both is fine?
Yeah.
Because when I'm going to change the presentation, they can see.
You need to,
Is it okay?
You need to trim each session to, for example, you should
نگاه
cut
کن
this.
میخوام جاشون که عوض کنم. مثلا الان پرزنتیشن یکه. خب پرزنتیشن کوشش اینه پایین کو
No, ببندش. Okay.
اینا میخوام بعدی رو کلیک کنم همه میبینم. اشکال نداره. اوکی اگه اشکال نداره پس اوکی. بذارین اونم چک کنیم یه بارم ببینیم که چیز رو شیر کنم. فقط ویندو رو شیر کنم ببینم فرقش چی میشه.
民事要讲的。
那们
我是这样，
OK，还有谁要讲？
小的他们
他们是第二个跟第三个，
是第一个吧？
不是
نه
是
اینجا
包含
همه میدونم
讲
ولی توی
讲
چیز
دیگه.
توی رکوردینگ جابجا که میکنم
第五
نمیفهم
那个和尚那个三两不能和
是吧？
我知道谁是第四个第五，
و چی باید این
他
کار
们是
انجام
第二个跟第
بدیم
三
لفظ
个。
داره
他们第二个、第三个、
对，
第四个、第五个，
Which time?
去问一下。
اوکی بعدا با هم حرف
我们两个
میزنیم Are you the first presenter?
Yeah, but
Is it
I
your
cannot
slide?
present in the first in the first
You want to
because
switch with swap with others with the force?
because the authors cannot come due to their visa is rejected, and they ask us to present their paper.
Okay,
But we have another paper in another room.
okay.
In the same
now
time.
what's the decision, the final decision?
Can we change to the last one?
Okay, he is a panelist. You should talk with him.
If the fifth one, he didn't know this earlier, he can't come here. So
I just provide yours.
this is the first
Yeah.
one, right?
Yes.
This is not the first one, this is the third one. Yeah, let's
the
just bring
second
up
one.
the first one. I'll see if I can present for him.
This is the first one.
Yeah, let me
Yeah.
do this. Yeah, I'll present for him.
Oh, okay.
Okay, so
I'll just look at the slides quickly.
Thank you very much.
Okay, so it's 10:30. Thank you everyone for attending this session. This is a graph foundation model session, so make sure you are in the right one. I'm Carl Yang, I'm a session chair. I just noticed that the first presenter is actually not here, and the people he found to present for him is also not available at this time, presenting somewhere else. So we would like to stick to the order, like the paper order. So people who have plans to attend the sessions to see particular papers won't be disturbed to come here to find not the one being presented, right? So in the last minute, I took this responsibility to basically present this paper for the author. Unfortunately, I've never read this paper before, and it's the first time I see this slide, so I'll try to do my best. Okay, so this first paper was work from Dr. Dr. Dong Xiaohe. I know the author pretty well. Her team in Tianjin University, yeah, so the work is on structural common sense driven graph contrastive learning. Oh, I'm going to do something. In the Zoom, right?
yes. So
Yeah.
share the screen.
Should be good.
Is it
Thank you.
okay?
Yeah, I'll play this. No problem. Oh, yeah, looking good. So, so this presentation contains 6 parts. I will start. Let's see. Just one moment while I try to put this on the side. So first introduce a background, and through a motivating experiment and example, we will show the existence of structural common sense in graph data and how existing methods have overlooked it. We will explain the proposed method, and we will discuss how it incorporates structural common sense into the model. Finally, we'll present the experimental results. So just as the theme of this session is a graph foundation model, our goal is to learn the model, to learn and model graph data. And it is well known compared to Euclidean data, graphs or structural data can effectively represent the connection relationships, which is ubiquitous in the world. Graph neural networks have achieved remarkable results in graph data mining and has many successful applications, such as social network analysis, recommender system, molecular prediction. However, the success of graph neural networks usually rely on large amounts of label data, while high-quality graph labels are often very expensive and time-consuming to obtain. Therefore, it is very important to explore effective graph self-supervised learning approaches. Which is also commonly used for like graph foundation models nowadays. So when talking about self-supervised learning, we must mention the successful graph contrastive learning objective. The classic graph contrastive learning paradigm relies on info NCE loss to generate effective node representations. This paradigm maximizes the similarity between positive samples while minimizing those similarity between negative samples. Based on this paradigm, there are currently many awesome works advancing the progress of graph self-supervised learning. Moreover, many graph foundation models now benefit from graph contrastive learning. Some of them use graph contrastive learning as their backbone, and some adopt the contrastive paradigm for pre-training. These trends show the importance of graph contrastive learning in the graph community. This thing is blocking the way. So far, lots of graph contrastive learning work has been proposed. They focus on improving graph augmentation, contrastive loss, and the generalization across heterophily graphs. However, most graph contrastive learning methods are black boxes. It remains unclear what kind of knowledge are truly acquired. More important for graph, it is uncertain whether the models are able to learn the structural knowledge inherent in graphs. This raises an interesting question. Can classical graph contrastive learning methods effectively learn meaningful graph structures? Can they align with human intuition? This is precisely the focus of this, this paper. So to address this issue, the authors began their investigation by focusing on misclassified nodes. They conducted an experiment using the classic graph contrastive learning model, GRACE, running it independently 20 times to observe its nodes classification results. The results revealed an interesting phenomenon as illustrated in the figure. As we may see, the authors show the statistics of misclassified nodes based on the frequency of their errors. For example, the value 18 on the vertical axis indicates the number of nodes misclassified 18 times out of the 20 runs. The horizontal axis shows the proportion of misclassified nodes relative to all misclassified nodes. To highlight frequent classification errors, the figure just includes nodes misclassified 15 or more times. Using the PubMed and Amazon CS datasets as examples, the authors found that across the 20 runs, the PubMed dataset had 1,437 consistently misclassified nodes, while the Amazon CS dataset had 804 such nodes. Both datasets show that these consistently misclassified nodes accounted for approximately 40% of all classification errors. This made the authors very curious about what kind of structural and attribute characteristics these nodes might have. The authors manually analyzed these nodes. They found that some of them could be correctly classified by noticing certain structural patterns. These patterns can be easily perceived by humans, while the models cannot learn. This reveals a critical gap. Graph contrastive learning relies on representation space constraints. It fails to account for foundational structural common sense. This common sense could help address persistent errors. Now let's turn to the simple yet unlearnable patterns through two examples. In this paper, the authors refer to these patterns as structural common sense. The left figure shows a pattern related to structural stability. The blue node, having many neighbors, results in a more stable embedding after message passing. In contrast, the pink node, with a limited number of neighbors, has an embedding that is highly sensitive to its neighbors, making it more likely to be misclassified. The right figure shows the pattern of differences between local and global structures. The greater the difference between a node's local feature and the global mean feature, the better its local linking pattern. In such cases, the node can retain its semantic after message passing. Conversely, when local and global features are too similar, the semantics of the node is easily lost during message passing, increasing the likelihood of misclassification. These two types of common sense are fundamentally very simple and basic. Humans can effortlessly perceive and understand them and could manually help correctly classify these nodes. However, current graph contrastive learning methods fail to properly classify these nodes. This led the authors to wonder, could we integrate the simple human perception into graph contrastive learning? Although these examples indicate that simple structural common sense cannot be effectively learned in graph contrastive learning, there are also critical accompanying challenges. These include two main questions. First, how can we represent structural common sense? And second, how can we embed structural common sense into the graph contrastive learning framework? To address these questions, the authors use a rule set to clearly and precisely define this common sense and use them to generate weights for each node. Furthermore, they introduce an additional rule representation to constrain node representations without modifying the base model, making their model easily pluggable into other graph contrastive learning frameworks. So now let's look at the overview of the model. As shown in the figure, the model is divided into the base model and the improved component. Here, the base model can be replaced by any graph contrastive learning method. The authors focus on using the constructed rule set to generate the weight for each rule. Then the authors utilize the proposed features to generate rule representations. In this context, the author primarily employs the representations and the corresponding loss constraints to guide the base model. Now we introduce two structural common sense proposed in this paper. The first is the neighborhood topological summation constraint, which focuses on nodes with fewer topological connections. For nodes with a smaller sum of neighbor degrees, we assign them higher weights. We express this rule using first-order logic as shown in the slides. The second principle is the local global threshold constraint. It focuses on specific nodes. These are nodes where the neighborhood features are ambiguously distinguishable from the global features. For nodes with neighborhood similarity close to the global, we assign higher weights. To facilitate understanding, this rule is also expressed using first-order logic. It is represented as shown in the slides. After computing the weights generated by the rule set, the authors aggregate them into a comprehensive weight for each node and multiply it by the corresponding rule representation. Once the rule representations are obtained, we introduce a representation alignment mechanism to match the mean and variance of the rule representations with the node representations. This process effectively integrates common sense constraints into the node representation. Next is the loss section. The loss consists of three parts, including the info NCE loss of the base model. The additional losses are the self-constrained loss of the rule representations. This loss pushes away different instances with the rule representations. For the alignment mechanism loss, it is to bring closer the loss between the rule and the node representations by minimizing the mean and variance of the two representations. So this loss enables common sense to constrain the base model. So here is the experimental section. This method achieved the best result in node classification, and the authors also integrated their approach as a plugin to existing classical graph contrastive learning methods, which consistently improved their accuracy. The following experiment corresponds to the error nodes analysis mentioned earlier. It examines the statistics of the high-frequency error nodes after applying the proposed method. As can be seen, the number of high-frequency error nodes is significantly reduced under their approach. So here comes the conclusion. The authors identified the limitations of existing graph contrastive learning frameworks, which primarily capture implicit semantic relationships but fail to perceive structural common sense within graph structures. They recognize that many nodes with fewer topological connections or lower feature distinctiveness are inadequately trained by conventional graph contrastive learning methods. They proposed their method to integrate rules to guide the model in learning human perceived structural common sense, while also providing a new direction for developing universal and efficient rule-based mechanisms and applying rules to existing pre-trained models. They introduced this alignment mechanism that enables the encoder to perceive this additional structural common sense, ensuring more comprehensive and effective training. In validation, they integrate their method as a plugin to multiple graph contrastive learning baselines, and their extensive experiments and visualizations demonstrate the effectiveness of their method. Thank you for your listening, and yeah, I'm very sorry for doing this more like a copy reader. So yeah, I guess we'll stop here because the authors are not here anyway, and I probably won't be able to answer many of the critical questions. So please feel free to email the authors. Yeah, and we have a couple of more minutes. So I think we will just wait and till like 48, we can start with the second presentation. Thank you. So where is the second presenter? Let's try to bring your things up. Yeah, we can start setting up. So at about 48, in 2 minutes, you can start. Let me try to find your, yes, it's not working.
Yeah, this one. Yeah.
Okay, just to remind everyone, we have like 5 papers in this session. This is a graph foundation model session. I'm the session chair, Carl Yang, from Emory University. And we have 5 papers, so we just finished the first one. Each paper will have 18 minutes in total, and 15 minutes for the presentations and 3 minutes for the question and answers. The presenters of the first paper were not here, and also the people they found to present the paper was also not here. So I took the opportunity to present the work for them. But now we are just 1 minute ahead of the time because of the lack of the QA. Soon we will have our second presentation from Xintong Yu from Singapore Management University. And this paper is about text-free graph foundation model. Yeah, we can get started.
Thank you for coming to the session, and I'm glad to share this paper with you guys. And in this paper, we propose a model called SAMGPT here, and I'd like to introduce this paper in these 4 parts. So first of all, let me introduce the motivation of this paper. So as we know that there are already some foundation models in the NLP domain right now, such as ChatGPT, Llama, DeepSeek. Well, so this motivates us to also build a foundation model in the graph domain because the World Wide Web is a huge knowledge repo. So there are many knowledge so that we could leverage them to build a huge foundation model. So it's raised a question is that can we build a universal graph model based on these various graphs, since these graphs may come from different domains. Some may be some citation networks, some may be social networks. So could we leverage the data, leverage this network from different domain to build a huge graph foundation model? So this is the question that we want to solve in this paper. However, it's not easy to build such a foundation model in the graph domain, because for graphs, on one hand, the feature of different domain is not aligned, because the feature meaning, the feature dimension in different domain could be different. But there has already been some work that aims to solve this problem. But also, on the other hand, in different graph domain, different graphs, they may have they may exhibit different structural pattern. So the structural gap also exists in different graph domains. But this challenge hasn't been solved in this in building a graph foundation model. So in this paper, our basic goal is to solve the structural gap between various domains here. Because if we don't harmonize these graphs from the structural gap in different graph domains here, they could conflict with each other. So even when adding more graphs from multiple domains, we can't lead to an improvement in the performance, but that will, in contrast, leads to a decline in the final results here. So in this paper, we want to build a multi-domain pre-training methods, and also we wish to transfer the prior knowledge to different domain here. So how should we do that? So on one hand, the challenge is in the pre-training stage, different domain, they could have structural gap. So we first wish to solve the gap in the pre-training phase, and then we need to solve the structural gap between these source domains, and we want to transfer this knowledge to another target domain here. So in this paper, we first propose structural alignment methods in the pre-training phase, and then we also propose adaptation, cross-domain adaptation methods for the cross-domain adaptation phase here. And firstly, for the multi-domain pre-training methods, before the structural alignment, we first need to deliver some feature alignment method, because we need to align the features semantic meaning at first. But as I have mentioned, there has already been some work aims to solve this challenge. So we simply follow some previous work to align the feature from different domain here. So in this paper, to align for the pre-training phase, we first leverage dimension alignment methods and feature alignment methods, same following previous work. And then towards the structural alignment, for each domain, we propose a pretext token. For each domain, we use a token here, as shown in this part. This token represents some domain-specific knowledge, which contains the prior knowledge of structure of some structured prior knowledge in each domain here. So we add this token to each layer of the graph encoder, because in the graph encoder here, each layer may represent some different level of the structured knowledge, because the one kind of typical graph encoder is graph neural networks, and they functions based on the message passing aggregation, and with each layer, they may aggregate hierarchical level knowledge. And so we add the structure token to the we use the structure token to guide the message passing aggregation phase here. So for each node, they could aggregate domain-specific structural knowledge for different domain here. And in this way, we could align the structural knowledge from different domain here. And then we simply stack the aligned structural knowledge from different domain here, and we aggregate with the feature alignment embeddings here to get the final overall embedding in the pre-training phase. And we use some contrastive learning methods as the pre-training loss. And then for the downstream adaptation phase, since the target domain could be different from the source domains here, so we also need to align the source domain with the target domain, and also we need to not only transfer a holistic prior knowledge, which means the knowledge from all the source domains, but also we need to transfer specific domain knowledge we need to transfer the specific prior domain knowledge from the pre-training phase here. So on one hand, we design a holistic prompt, which is simply certain learnable vectors here used to transfer the unified holistic prior knowledge to the downstream part. And it also works by guiding the downstream message passing phase here. And for to transfer the specific prior knowledge from each specific domain, since some source domains could be more important to the target domain because they could be more similar, and some target domain and some source domain could be more unsimilar to the target domain. So we need to weight the importance of those different domains here. So we use so how do we categorize the importance of different source domains here? In our work, we use a specific prompt here. The specific prompt it's the aggregation of the pre-trained domain tokens here. Since each domain tokens, they contains a specific structural knowledge from each domain here. So we learn the aggregation of these domain tokens, and we aggregate them to obtain the specific prompts for the target domain here. And we use the specific prompt to adapt the prior knowledge from multiple source domains to the target domain here in our work. And then we fuse these embeddings to get the final embeddings on the target domain. And also we leverage the feature adaptation methods to adapt the prior feature knowledge from different domains to the downstream target domain following previous work, such as this work. This is also our work which propose feature line methods towards the building a graph foundation model here. So if you are interested, you could also take a look at it. And by using the SAMGPT here, we could achieve the best performance compared to previous work, no matter it is a graph foundation model, such as Jacob, or some cross-domain adaptation methods, or the pre-training and prompt learning methods, on both one-shot classification task and graph classification task here. And in our experiments, we use 6 data sets as the source domain, and we use the last one as the target domain here. And we also vary the short number for the downstream classification task here. And you can see that for generally for all short, SAMGPT could achieve the best performance. And we do some application study here. First, in table 3, we increasing the number of source domain. And you could see that for these two competitive baselines, even adding more source domains, the performance won't generally be better. But for our methods, when adding more source domains, the improvement continually, the performance continually improve. And we also do an application study on the key components of SAMGPT here. So you can see that with the structure tokens, the holistic prompts and the specific memory are all important in our designs. Without either one, the performance could decline here. So that's all. And this is the link for our paper, and this is the QR code for our paper. And by the way, I'm right now a postdoc at Singapore Management University, and I'm looking for another postdoc position start from next year. So and this is the QR code for my homepage. So if you are interested, please connect me. Thank you very much. So any questions?
Do you compare to Ultra? Because that seems to be like the most famous graph foundation model that I'm aware of, at least.
Sorry, which graph foundation model?
Ultra, its name.
Oh, yeah. So when we submit this paper, I think that model hasn't been published or its code isn't open source, but we will compare with. Really, yeah. Okay, I see. We haven't compared it. We haven't compared with it right now. We will compare with it later. We thank you for pointing this out.
And it has been around for a while.
Mm-hmm.
So at least 24, it has been published. Yeah.
Okay, I see. So we will check this later.
So yeah, we've been like thanks for the great presentation. So we've been like following some of the graph foundation model works as well. One of the things we found was it is pretty hard to really like define the boundary of what data sets we use to really train a so-called foundation model, right? Because the graphs are pretty flexible, and there are really data sets, graphs constructed from different domains, different data, right? Really having rather different patterns, right? Unlike language, right? Language always have like some patterns, right? But graph have very different patterns. So my first question would be, what are the data sets you use to train your like so-called foundation model?
Oh yeah, we simply use some text-free graphs here. So the data we use are graph without text, only the topological data, only the topological structure and their graph features here. No
So
features
basically, you train your model over these 7 data sets and test it on each of them.
We train on 6 of them, and we test on another one. Another one is served as the downstream target domain here.
I see. And these graphs were not text-free like originally, right? So you just remove the text and you want to fully rely on the structure to make those predictions.
Oh yeah, right. And so in this work, we focus on the graph, the topological things. Since some graphs they lack text data, so in our work we only focus on text-free graphs here.
Right, that's interesting, because these data sets we know the text contribute a lot to the prediction, right? But anyway, I think this is your like the way you intentionally to set it at this. The other following up question would be, do you have any analysis regarding how the different data sets really contribute to a specific data set, right? Let's say you use Cora to do the testing and you trained the model on the other 6, right? How do they help Cora, right? Is there any insight about why do they help, right?
That's a pretty good question. In fact, we are trying to do some future work about this part. And intuitively, I think that if the target domain is a citation network, for example, then some other citation network as source domain could contribute more to this target domain, right? But as you see, this is a very interesting question, and we wish to do some future work to find if other kinds of source domain data could contribute to well some similar or more different domain if there any connection with between them.
Right. I think basically it is good to understand because you also like describe in your model is somehow able to weight the different the data from different domains, right?
Yeah, right.
So it's good to understand how these weights are really are, right? And also if you are going to test like data from really different domains, right? Rather like this, other than this kind of all similar kinds of networks, if you really use graph data from more different domains, right? How much do they really help? I think the community will benefit from this kind of research, basically showing like graph data probably is how it is different from like a language or other type of data that really makes the foundation model doable or not, right?
Right, exactly.
Okay, any more questions? Okay, so we are right about the time. So yeah, let's thank the speaker again, and we'll start with the third presentation. So the third presentation is also about graph foundation model. It's given by Li Sun from North China Electric Power University.
Okay, thanks, Carol. Thanks for the introduction. I am Sun Li from North China Electric Power University. And first, thanks all my co-authors. And recently, large language models such as GPT-4 makes a revolutionary advancement of the foundation model in language realm. And graphs are omnipresent non-Euclidean structure ranging from recommender system and biochemical structures. Unlike word sequence in the language, graph present distinct non-Euclidean structure encapsulating the complex intercorrelation among objects, which prevents the direct deployment of LLM. And the graph neural networks achieve the state-of-the-art performance on learning graph data, but often lack the generalizability. The GNNs are often designed for specific tasks, and retraining is typically required on different tasks or data size to maintain the expressiveness. Consequently, graph foundation models are emerging as an interesting topic. We want to have one universal model that can be applied to different graph data size. Compared to the great success of the foundation model in other domains, the GFM is still in an early stage. The existing startups primarily focus on the text attributed graphs, and the structural knowledge is coupled with the textual attributes of the language description, and the transferability relies on the commonness of the text or language. What if the real graph does not contain the fruitful textual attributes? And the sequential graph description tends to fail in capturing the structural complexity, which is the predominant characteristic of graph. In fact, the graph structure is quite complex. Tree-like in some region and the linking in others. Motivated by the aforementioned limitation, we raise the important question: can we go beyond the large language model and pre-train a universal model to learn the structural knowledge for any graph? And this is the key motivation of our work. We want to learn a graph foundation model from the structural knowledge The answer to the foundation model in language or vision domain is a shared vocabulary, maybe. There also exist the common substructures underlying the graph domain, and we introduce the concept of the structural vocabulary by which any graph can be constructed. And we gave a more formal description here. And we leverage a simple yet effective structural vocabulary, trees and cycles, to build the graph structure. Furthermore, we explore the inherent connection between the structural vocabulary and Riemann geometry. More specifically, the hyperbolic space aligned with the tree structure and the hyperspherical space is more suitable for the cycles. And herein, the question is how to model the structural vocabulary of trees and cycles to the corresponding Riemann spaces. And our solution is the product of the tangent bundle. We introduce the notion of tangent bundle to incorporate the information of the precision in the manifold and the pattern of the different trees and cycles. And we use the condition, it's not a tangent bundle, we use the condition product to incorporate the information of different structures. And then we gave a formalism of the product bundle, and more specifically, the coordinates in manifold contains the relative precision of a substructure, namely the tree and cycles, and the encoding tangent space carries the information of the global structure. So this is how we use the product of the tangent bundle for the modeling of the graph data. In our model, we first sample the substructures, and then we use a vocabulary learning module to model the substructures, the relative precision, and the patterns in the substructures. And then we use a global learning module to encapsulate the information of one node around the graph. And finally, we use a geometric contrastive learning for the self-supervised learning of this pre-trained model. And the name of our model is RiemannGFM. Before going to the details, we actually need some operations in the constant curvature spaces. And I will not go through the details and derivations. And we use the Lorentz-like multiplication or the matrix left multiplication for the linear operation. And we use the geometric midpoint for the aggregation. They are generic to any constant curvature spaces. For the vocabulary learning module, it performs the cross geometry attention to embed structural vocabulary into the constant curvature spaces, regardless of specific graphs, which offers the shared structural knowledge for the cross-domain transferability. In the cross-geometry attention, the key is the query. The query is from the counterpart geometry, and we will show its effectiveness in the abelian study later. And the global learning module, after we sample the multiple substructures from the graph, this module examines the entire graph, overlooks the entire graph, to finally learn the node encoding from a global perspective. And the key challenge here is how to exchange the information from different tangent spaces, because the embeddings, the encodings are in the bundle, is in the tangent spaces of the different tangent spaces on the manifold. And our solution, we introduce the bundle convolution where we use the parallel transport to find the common tangent space for the information aggregation. In Riemann geometry, the parallel transport with respect to the LC connection transport a vector in the tangent space to another tangent space with the linear isometry. And the further details can be found in our paper, and I will not go through further details here. And finally, we use the geometric contrastive learning, where we use the hyperbolic and the hyperspherical geometry as a different geometric view so that we can conduct the contrastive learning before different geometric view. And in the experiment, we compare with these GNNs and some representative of the self-supervised graph learning models, and the graph foundation model include the 1-for-all, the GCOPE graph ANI, and AGA and Open Graph. We examine on the text attributed, mixed attributed, and non-attributed graphs, and we want to examine that the structure knowledge is important, and we can build the graph foundation model from the structural knowledge. And we use the link prediction and node classification as a downstream task. And first, we examine the cross-domain transfer learning performance, and we achieve the best results for the node classification without text attributes, because in our pre-trained model, we do not include in model the textual information here. And for the link prediction, we achieve the best results compared with this specialized GNNs and other graph foundation models. And also we examine the few shot learning performance, where the node classification is as the downstream tasks. And we consistently achieve the best performance here in both 1-shoot and 5-shoot settings. And as for the product of the tangent bundle we use, we have a geometric ablation. Here we want to examine the alignment between the hyperbolic space and the tree structure, and the hyperbolic and the hyperspherical space and the cycles. And here, this is the results of our geometric ablation. Also, we include a variant of the single geometry attention, where we want to examine the effectiveness of the cross geometry attention in our design. And then we have the experiments on the impact of the pre-training data set. We adopt the Flickr Amazon Computer WikiCS data set as a pre-training data set respectively. Here for example, we pre-train our RiemannGFM on Flickr, and we test the model on either PubMed and Airport. And our proposed model shows more stable performance over different pre-training data sets. And we also examine the encoding of our graph foundation model, the expressiveness regarding the link prediction. And it shows that we achieve competitive or even superior results compared to the specialized model trained on the data. And here the results is we use the encoding of the foundation model pre-trained on Flickr. And finally, we show the a clustering results with TS and E. And the structure embedding presents the clustering pattern as well. And finally, in summary, we explore the graph foundation model for a wider range of real graphs, not limited to the text attributed graphs. And we study the graph foundation model from the structural geometry for the first time to the best of our knowledge. We propose a universal pre-trained model, the RiemannGFM, on a novel product bundle where the structural vocabulary is learned in Riemann manifolds, offering the shared structural knowledge for cross-domain transferability. We evaluate the superiority of the proposed model in cross-domain transport learning and few-shot learning on a diversity of real graphs. And this is the link of our code. And thanks for your attention. Any questions?
Thank you for your presentation. Well, just start with this basic structures to create a graph. That is basic structure are trees and cycles. But my question is, how do you identify these basic structures? Are you applying an algorithm to decompose a given graph into a specific these specific structures? What is the missing step to identify these basic structures in a graph?
Okay, thanks for your question. I think it's a very, very good question. And for the structures, the trees and cycles are very simple and omnipresent patterns in the graphs. And as for trees, we can sample from the 1 and 2 hop neighbors, and it is a trees. And for the cycles, we can randomly sample the triangles and some simple cycles. So it is easy to be implemented to sample the substructures or the common substructures. And it is a very good question that maybe we miss some pattern. On one hand, some of the similar pattern can be compensated in the Riemann geometry for the hierarchical and selective structures. On the other hand, it is a fact that some of the structures are missing. Maybe we can further enrich the structural vocabulary, and it may be left to be the future work. Thanks for your question.
So I wanted to ask a few questions. So the first thing is, yes, great work. And using the Riemannian geometry to kind of characterize the shareable structures, right? I think it's a very interesting idea. My question is, first question is on the more like technical part. You drew very good pictures, but I didn't quite understand like how you really use the Riemannian like geometry to characterize the structures. I mean, did you learn like a few different kinds of kernels, or did you have like different kind of parameterizations for the Riemann geometry so they can like basically they can correspond to different kind of substructures? Or so basically, is it some kind of learnable kernels, or is it a few numbers of different like parameterizations? How is it implemented?
Basically, we imbibe the different substructures into the constant curvature spaces.
I mean, sorry to interrupt. I mean, like when you say different structures, do you define a couple of them, or do you have one like a parameterization to basically fit to each of the nodes?
We do not fit for each of the node that for all the tree structures, we fit the tree structures to the constant curvature of the hyperbolic space. There is some there isn't a learnable kernel, but we use the Riemann metric or the distant metric. And similar for the cycles in the standard curvature of the hyperspherical space. If we learn the manifold for each substructure, it cannot be a foundation. So we feed the different substructures into the fixed constant curvature manifold. So every new for any new graph, they can be used in this a standardized manifold construction. So this is the
If you only have one like fixed manifold, how do you like accommodate the different structures? So do they reside on the different places, different places in the manifold?
yes, and we have different Cartesian product, and so the constant curvature spaces are there. They are standardized, but we create a product bundle to incorporate the different structures.
I see. Okay. Yeah, thank you. I think, yeah, I do have following up, but we are about the time, so I'll follow up like
Okay.
privately. And so let's thank the speaker again. And yeah. Do I see the fourth speaker here? So yeah, can I see your name first? Yeah. So yeah, the fourth presentation is from Zhibing, from Tsinghua University. I think it's on some unified graph classification model.
Hello, everyone. My name is Jivini. I'm a graduate student from Tsinghua University. It is such a pleasure to be able to present in the web conference and this specific session here. And I am the first time to present my speech orally, so if I don't know how to respond to your question, please give me some time. Perhaps I will use my translator. The paper I will be presenting today is titled FG-CIBGC, a unified framework for fine-grained and class-incremental behavior graph classification. My presentation today is divided into the following 4 parts. Firstly, I will talk about the research background of our work. Then I'll introduce our proposed method called FG-CIBGC. Later, our experimental results will be discussed. Finally, several conclusions will be made. As we all know, sophisticated attacks increasingly threaten the global internet infrastructure. As graph offers an ideal representation for security investigation, analysts often transform audit logs into a large, unified graph containing numerous operations by the web services. However, navigating and investigating the large-scale graph presents a non-trivial challenge of heavy analysis workload. Behavior graph classification addresses this challenge by partitioning large graph into a set of smaller behavior graphs, each corresponding to a specific web service operation, and subsequently classifying them, enabling security analysts to focus on a few representative behaviors. And this tool, behavior graph classification, has emerged as an indispensable technique for various security investigation domains, including post-intrusion detection systems, vulnerability detection. While it sounds promising, the research communities have uncovered a series of limitations when implementing the existing approaches in real-world scenarios. By summarizing those issues in this figure, we recognize the following 2 main challenges. The first challenge is fine-grained emerging behavior graphs. Prior learning-based proposals in this domain rely solely on coarse-grained behavior graphs. That is to say, while these methods can ascertain whether a behavior graph is related to a specific internet service, they lack the granularity to differentiate between distinct operations of that service. Consequently, the primary challenge lies in developing a methodology for fine-grained behavior graph partition. The second challenge here is incremental model adaptations. In real-world scenarios, behavior graphs evolve in an incremental manner, presenting the requirements of class increments. Class increments refers to emerging novel classes that should be incrementally updated into the model to become known classes subsequently. In production environments, continuous service updates introduce novel behavior graph classes unknown to analysts, also known as the open world issue, actively detecting and attaching new classes to a model's knowledge base without catastrophic forgetting is a significant challenge. In this paper, we propose the first unified framework called fine-grained class-incremental behavior graph classification, aiming to enable the fine-grained behavior graph partitioning and incremental updates with novel class detection. In summary, this paper makes the following three key contributions to analysis of current learning-based behavior graph classification proposals. We identify two critical challenges that impede their deployment. To tackle this challenge, we propose this method, which is the first unified framework for fine-grained and class-incremental behavior graph classification. We designed two components for FG-CIBGC, thereby realizing the fine-grained behavior graph identification and incremental model updates with novel class detections simultaneously. And we construct a new benchmark that satisfies both completeness and diversity, featuring 3 log types and 992 graphs across 32 classes, as well as a new ERU metric for fine-grained evaluation. Next, I will introduce the proposed method. As shown in this figure, the proposed consists of 2 novel components. The first component is used to achieve fine-grained graph partition. The second key component is utilized to conduct incremental model adaptation. First, the G-partition module is proposed to learn the correlation of multi-source logs in the prompt and finish the log correlation. G-partition builds on the ICL paradigm with LLMs. The derived behavior units are then used to partition the audit logs into fine-grained behavior graphs, which are subsequently reduced to achieve greater compactness. Second, G-adapt is proposed to proactively detect both known and unknown classes, classify them accurately, and correspondingly update the model in an incremental fashion. This is especially achieved through the combination of OO detection and the class-incremental graph learning. Let's see the challenge analysis of the first component. Audit logs alone can contain only low-level information about the system activities of web services, lacking the necessary knowledge to partition them into fine-grained operations. To accurately capture operations, the research communities observe that introducing logs with high-level semantics of a more promising solution. Therefore, a vanilla method would be to leverage the existing log correlation approaches to correlate these diverse log sources. However, prior log correlation techniques rely on static correlation rules and overlook the potential for different logs to describe the same operation. This renders the use of logs with high-level semantics to partition audit logs into fine-grained behavior graphs a fundamentally new task. Therefore, our method rationale would be to learn the correlation of multi-source logs in a prompt and finish the log processing process. To address this challenge of multi-source log correlation, we resort to the in-context learning paradigm of large language models, as LLMs have demonstrated superiority in log processing tasks, but they have never been applied to log correlation tasks. In this paper, we observe that the audit logs contain execution information, APP logs, that is application logs, contains the event boundaries, and the network logs represent network connections. They can be correlated to form behavior unit. Each behavior unit represents the complete set of multi-source logs generated by a single service operation. RCL with LLMs not only enable mining of the latent semantic correlations across multi-source logs, but also have the advantages of rapid deployment and easy interactivity without large tuning cost. Prompt strategy is the most significant part of RCL. In this paper, we propose a novel type position-aware prompt template specifically designed for log correlation tasks. To pre-process the influx of multi-source logs before prompting, we first pass the logs into standardized forms. After that, we merge these parsed logs in a canonical order and segment them into batches of 400 entries. This approach considers that the logs presenting the same web operation are typically temporally close, and services related operations do not correlate with an excessive number of logs. It should be noted that this component is coupled with a warm-up mechanism that enhances the ICL capabilities of LLMs. Let's see the next challenge analysis of the second component. A vanilla design would be to directly apply an existing class-incremental graph model. However, existing proposals face impracticality in real-world scenarios due to unpredictable class increments from expanding system operations, a critical open-world challenge largely overlooked. To detect unknown classes, OD detection is shown promising potential recently. However, existing works only finish partial of the task requirements. That is, they only tell if a given behavior graph is OD, but cannot assign label to them, so making it incapable of attaching new classes to the model's knowledge base. Besides, they do not consider the challenge of human in the loop. Therefore, the mentioned rationale would be bridging the gap between OD detection and the class-incremental learning. In terms of outlier detection, we use OD detection with weakly supervised reference feedback to allow analysis to be human in the loop. We introduce the hyperparameter Q, which is the domain iterator value of the expected ratio of new OD behavior graphs in the next time step. For new class samples, we utilize a k-means-based clustering algorithm for class annotation to increase efficiency. Due to uncertainty in unknown class counts, naive k-means is incapable, prompting the need to explore reference values for determining k. Fortunately, we observe that the lower bound of k is defined by distinct application log types, as logging constraints and attack complexity may cause similar logs to reflect different behaviors. Thus, the number of different application log types can serve as a reference value. In terms of the model updates, we choose the disentangled model as a backbone, considering its effectiveness and efficiency. Besides, to enhance model adaptability to structure and class increments, we adopt a replay-based incremental learning strategy utilizing class prototypes. Next, I will present the experiment results. The dataset of FG-CIBGC evaluation must include the complete log sources to enable graph and behavioral graph identification without pre-obtained knowledge. Besides, it should encompass diverse system behaviors to enable thorough evaluation. Given this situation, we construct a new behavior dataset that satisfies both properties featuring 3 log types and 4,406 graphs across 31 classes. Besides, we consider a novel fine-grained evaluation metric ELU inspired by MLU in semantic segmentation. We propose ELU, a novel metric designed to comprehensively evaluate methods by capturing fine-grained requirements. The main experimental results show that the FG-CIBGC outperforms baselines across all data sets, achieving an average improvement of 4.89% in ELU, and FE score according to the baselines. The superiority is largely attributed to the combination of both the aforementioned two components. The ablation study results validate each component, and we also conduct experiments to assess whether the proposed FG-CIBGC can indeed generate fine-grained behavior graph classification results that are effective in facilitating the downstream attack investigation task. As shown in the picture, it is evident that FG-CIBGC demonstrates the best performance in fine-grained behavior graph generation, thereby optimally facilitating attack investigation. We also perform hyperparameter sensitivity analysis on 3 representative datasets. In conclusion, this paper presents FG-CIBGC, the first unified framework for fine-grained and class-incremental behavioral classification in internet services. To validate the efficacy, we introduce a new benchmark, and the extensive experiments demonstrated its superiority performance on fine-grained and class-incremental behavioral classification tasks. So thank you. Any questions?
So, do we have the fifth sprint? Yeah, so the fifth presentation is by Wenxuan Guo from Shanghai Jiao Tong University. And the presentation is about, it's about a unified and generalizable reinforcement learning for facility location problems and graphs.
Thanks for the introduction. I'm Wenxuan Guo from Shanghai Jiao Tong University, and I'm currently a PhD student. And today I'm happy to present to you our work, Unified and Generalizable Reinforcement Learning for Facility Location Problems on Graphs. So the facility location problems, or FLPs, are a family of optimization problems that we may encounter in everyday life. And the task is about optimizing the placement of facilities to meet the demands efficiently. And you may think about how to place the charging stations, the schools, or the bike sharing stations efficiently. And specifically, our work focused on the graph-based settings where the nodes represent the customers or their needs, and the places of the potential facilities, and the edges of the graphs represent the travel routes between the nodes. And it is important to mention the graph setting because the graph distance is usually different from the Euclidean distances, and our work used the GNNs to process this complex graph structures. While this is a long-standing problems, it is still challenging because it is NP-hard combinatorial optimization problems, which means there is no polynomial algorithms to find the exact solutions, and the mixed integer programming solvers cannot scale to large instances. And sometimes we need to find, for example, in emergencies, we need to find the solutions fast rather than find the optimal solutions. And let's review some of the prior works, which mainly fall into 3 categories. The first line of works is to solve them by the exact solvers, like MIP solvers. They can find exact and optimal solutions, but they're too slow for large or in the time-sensitive scenarios.
And the second line of works are the classical heuristics or meta heuristics. And most of them are trying to balance between the speed and the quality of the solutions. And recently there are some emergent machine learning approaches which are mostly constructive, which means they build the solutions step by step. And this way of constructing solutions is inheriting myopic. And this work typically assume the simpler Euclidean space. And moreover, they often demonstrate poor generalizability to the different graph sizes or the other parameters. And our work is at the intersection of the second and the third categories, where we take an improving heuristic style while using the machine learning techniques to help find the intelligent strategies. So now I will introduce two types of the facility location problems. The first one is the p-median problem, where given a graph with nodes V and edges E, and there is a node demands at each node I, and we also have the pairwise distance between every two nodes. And our goal is to find P facilities on the graphs to minimize the, we can look at this formulation. It is actually the sum of every node demands times the nearest facility to that node. And similarly, there is another facility location problem, which is facility relocation problem. On top of the p-median problem, we have extra input, including an initial facility set F0 and a budget K, which means we can relocate up to K facilities to reduce our objective function. And we can measure the performance of FRP by an improvement ratio, which is the reduced objective function over the original objective function of F0. So these two problems, PMP and FRP, are related, but they are often solved by separate solving strategies. And our work proposed a method called PPO swap, which is a unified single framework that can tackle both PMP and FRP. And it is an improving style solver, which means it iteratively improves an existing solution via swaps. And we also leverage reinforcement learning, which we train an intelligent agent that learns to swap with the large reducing the objective function. And the agent is trained using proximal policy optimization. And lastly, our method is graph aware, which means it has specially designed graph components to understand the complex graph structures. So now let's look at the formulation of our of PPO swap for the relocation problem. We define the state of the problem with two kinds of features, including the static feature, which consisting of the node coordinates, the node demands, and the graph topology. And there are also dynamic features, which changes as the current solution change. They include the facility indicator and some assignment variables that may change as the facility changes. And we define the action as a relocation pair and the U1 is the facility to remove, and U2 is the new place to put a facility. And we define the reward of a step as the delta improvement ratio. So this is the formulation of the relocation problem. So now we have a strategy to solve the relocation problem with reinforcement learning. We can then extend it to the p-median problem. And as shown in the figure, we just need to provide an initialized solution where in our work, we use density-based random solutions. And then we can call PPO swap for relocation as a subroutine. And it will improve our initial solution, and hopefully we get a better solution. And we will repeat these trials for multiple times and keep the best solution as the final one for the PMP. And if we look inside our architecture, there are some key components, including an actor-critic architecture, which is standard in reinforcement learning. And we use graph neural networks as our encoder that extract useful information to represent each node. And to select the relocation pair, we use an attention-based mechanism to find the facility to remove and to insert. And finally, we design some Voronoi-aware features, which means they are based on the Voronoi graphs divided by the current facility set. And here I'll present some results. And first is about the scalability. Our method is trained on graphs with 100 nodes. And as you can see from the figures, it's this purple lines is the result of PPO swap, and the running time of our method remains nearly constant, even when it scales to large graphs of 1,000 nodes, and it achieves competitive solution quality compared to some classical heuristics. And on the right is the results of the p-median problem, and yeah, it still presents very strong scalability. And this page, we perform some experiments to prove the generalization ability. And on the left, we compare to another machine learning-based method, SPONet, and it is a constructive method. And both of the methods are trained with the fixed parameter of p equals 15. And as we can see from the figure, the performance of SPONet may degenerate very largely when the parameter changes. And our method seems to generalize better. And on the right, we modify the SPONet to test the effects of our graph-aware design. And it seems like our method can learn better when the facility number changes. And we also perform some experiments on the real-world Shanghai road network. So the gray layer is the road network of Shanghai, and the red nodes represent the demand distribution, and the blue crosses are the facilities generated by different solvers, and the left one is generated by Gurubi, an exact solver, and in the middle is our work PPO swap, and on the right is the simulated annealing results. And the our work not only generate solutions with low objective function, but also we can see that visually they generate a the solution is closer to the Gurubi solution. And in conclusion, we propose PPO swap, which is a unified RL-based framework for facility location problems on graphs. And our method have several advantages. It is able to generate fast and scalable solutions, and it can generalize across the instance sizes and parameters. It is also graph native, which means it effectively handles complex graph structures. And it is a unified framework for both PMP and FRP. And that is my presentation today. Thank you for your attention. And our code is available at GitHub. And our work will also be presented in the poster session this afternoon. So if you are interested in our work, we can have more communication. Thank you.
Okay, so that's the end of the session. Thank you again for coming to the presentations, and thank you for everyone who presented here as well.